Start. All right. So on Friday, we went through this example of allylic bromination. We started, excuse me, with this example right here, where we took this alkene and treated it with NBS and UV light. And under those conditions, we get allylic bromination, which is a strategic method for putting a bromine at the allylic site of an alkene. All right, so it's a way, again, under the larger umbrella of alkyl halide synthesis. Allylic bromination is one of those methods to make alkyl halides. All right, so let's look at another example, because I think we walked this one down pretty good. We went over some of the key points, and one of the main points is that if resonance is possible, resonance is going to happen. So you're going to get those intermediates during the propagation step that actually can rearrange by resonance to give you new intermediates. And whatever intermediates you generate in propagation, they will all be terminated. What we missed was the last part of the question. And I asked y'all to look over this or think about this, excuse me, over the weekend. It says, what product would you expect to be formed the fastest? Now, in that video that was sent out, the answer to that question was actually in that video. So somebody tell me what the answer to this question is based on these products that we have right here. So these are our 4 products. Which one do you think is going to be formed the fastest?
The one with the least substituted.
The least substituted. Excellent, excellent, excellent. So you're really going to have a competition between this product, because that's a primary halide, this product, which is also on a primary carbon, and this product right here, which is also primary. So all 3 of those are going to be competing with one another for the fastest product form. So with allylic bromination, the rate of, put the date in, what's the date? The 24th. So the rate of the reaction is based on the substitution of the radical. I'm gonna say they're allylic radical. Right, so less substituted radicals terminate faster. Right, so all of these are primary. Right, so that's primary. This is also primary. And this is primary. So it'll be a competition. Move that over.
Dr. Russell.
Go ahead.
Can you scroll down back to the sentence you just wrote?
So the primary radicals are going to compete to see, they'll compete for the fastest form product. So in that case, you're going to get basically a distribution between those 3 primary carbons as to which one is the fastest, if that makes sense. All right, any questions about that? If not, we're going to move on to the next example, and we're going to do the mechanism for that, go through it step by step. And then we have actually have 2 other examples for this. and we'll do number, we'll work through all the rest of these. And that'll take up the rest of this class period. All right, any other questions about that top example? All right. So I'm gonna cut this out because we're gonna need room to do this. So this is just a basic question. For the following two reactions, draw all possible products. And for reaction one, propose a mechanism. But we're gonna do the mechanism for both. So let's do that. Let me add a page. All right, so what's the first thing we need to do here before we do anything? So the strategy for these types of problems is to do what? We're doing, again, based on the conditions. This is an allylic bromination. All right, so what do we need to do first before we even attempt a mechanism or anything like that?
Do we have to find the intermediate?
Not the intermediates, find the reactive sites.
Oh,
Yeah, you got to find where the reaction is going to take place. That should be the first part of your strategy. If you know it's a allylic bromination, and this is the giveaway, NBS and light, that's and an alkene, that's telling you that it's going to be a allylic bromination. First thing to do is to find the reactive sites or the allylic sites. So here is going to be where? Help me out.
Is it gonna be the CH3 on the left by the double bond?
Okay, great. Here.
Yes, sir.
Where's the other one?
One pointing upwards to the right of the double bond.
Right. So those are your two allylic sites. So you know you're going to get how many products?
4.
Good. All right. So your number of products is going to be equivalent to 2 times the number of allylic sites. Why are we going to get 4 products and we only have 2 sites? Let's rationalize this. Anybody?
Because you can do resonance with each site.
Resonance. When you make the allylic radical in propagation, it can do resonance and give you 2 new radicals. So you're going to get a total of, you're going to get a total of 4 allylic radicals in propagation. All right, so let's go through the initiation part. We know what that's going to look like. That's just going to be MBS homolytically cleaving to give you a bromine radical. We don't really care about this step. But when you shine UV light on it, that's what happens. All right, so that's that. We got a lag. Come on. Let me document this time. I'm about to AT&T about to start prorating my internet. Let me switch. I'm not even gonna fool with this thing. Let's see. Hotspot. Just give me 1 second to switch my internet source because this is I got to cuss somebody out today, but not really cuss them out, but you know, give them a piece of my mind. This is ridiculous. All right, let me switch on my iPad too. Give me 1 second. Right. So now we have our bromine radical, and that's what's going to do the abstraction in the propagation step. So let me just copy this right quick. Where do you want to start?
We can start on the one on the left side.
Here.
Yes, sir.
All right, I'm gonna white out the hydrogens right quick so I can draw them out. 1 second. I'm gonna write those in actually. So now I have a bromine radical, and then again, this is not new, right? We know what's going to happen here. The CH bond, let's take this one, is going to cleave like so. And this is, anytime you're confused about the propagation part, just remember that you're going to take one of the CH bonds. They're all equivalent, so it doesn't matter which one you take. You're going to take one of those bonds, you're going to break it homolytically and give 1 electron to each atom, right? So on the other side of the arrow, you have to have a radical wherever you pull that hydrogen off of, right? So that's that. And then I'm going to bring this arrow here. So as a side product, I'm going to get HBr. And we'll get that for every one of the propagation steps. And then we're going to get this. Let me see if I can catch that. Nah, never mind. I'll just draw it. We're going to get this radical right here. Right? Anybody not see that? Where that's coming from? All right. So that's one radical. What now? Somebody tell me with this radical right here, what is the resonance form going to look like? Because it's going to do resonance. Go ahead, Tosh.
Do you break the double bond? Then does one of the radicals go down? I mean, does one of the but one of the radicals go down to the radical below C, below carbon?
Right. So we're gonna let me make it. You're right, but let me make that as plain as possible. When you have an allylic radical, which means you have a radical adjacent to a double bond, what's going to happen, the way that delocalizes every single time is you shift the double bond over. So let me erase these arrows. You see where the radical is right here? The double bond is going to shift to here. And then the radical is going to end up here on the other carbon, because there are 3 carbons in this unit, right? We have this carbon, this one, and this one. So that's those 3 atoms are going to share that electron. All right, so let's go back. But you're right, that's what's going to happen. But you know, it's also a way to think about it is if it's next to a double bond, you're going to shift the location of the double bond and then shift the location of the radical. So this is going to come here. That's going to put my pi bond right there, because those 2 electrons coming together between those 2 carbons will put the pi bond there. And then this last electron in the pi bond is going here, right? So this carbon is going to receive that 1 electron, and then these 2 carbons are going to be where the new pi bond ends up. All right, so then I'm coming here. Now I have this, where my double bond is now here on the end. And then here, now my radical is here. And that's my resonance. That's what that resonance form looks like. All right. Questions about that? All right. Now let's look at the other hydrogen, which is right here. Let me see if I can steal this. Nope. Nope. All right, I'll just redraw it. So here we got actually, let me just steal the one from the top. All right, so now we're going to work on this end right here. We know we have a hydrogen here. All right, so that's where my reaction is going to take place. That's where the abstraction is going to happen. All right. Same pattern of electron flow. It never changes. Never changes. This arrow's coming here, and then you're going to break the CH bond like so. All right, to leave a radical on the carbon. I'm going to put this here, put a radical right here, plus what?
HBr.
Plus HBr, right? That's a side product. Every time you do an abstraction and a radical reaction, you're going to get a HX as a side product if a halogen is your initiator, in which in this case the bromine is the initiator. All right, so now that's that. Now what's going to happen here? Resonance. I'm asking that as a almost as a rhetorical question, because I have a allylic radical right here. I have an allylic radical, and anytime I have that, you'll be able to do resonance. We're going to talk about another consequence of the resonance with this example right here. All right, so now we can break, not with that pen, we can break this up like so, shift that double bond over, which is what we always do with that allylic radical. So that's that. Double bond is now here. All right, so now I got 4 radicals from propagation. And now I'm ready to terminate. So I can go ahead and do the termination step. And I'm just gonna redraw the radicals. Just copy that. So that first radical we had here, The second one we had here. No. Like that. We had a radical here. And then for the other one, we had a radical here. And one here. Is that right?
Yes.
Let's label them. This is, we'll call this A, B, C, and D. All right. Now, let me ask this question. Let's go back to the previous example. Which one do you think is going to give you product the fastest? This is a little easier to see now, or should be, right? Because this is a primary allylic radical. That's secondary. This is tertiary, and this is also secondary. So when I terminate these, which one do you think is going to terminate fastest?
Would it be A?
A, because it's the least substituted. All right, so this is going to give you, let me cheat. And remember, we're not terminating with HBr, right? That's a no-no. We are terminating with a bromine radical, which I need to put the electrons in to make that official, right? There's a radical here, right? And those two are just going to come together like so. Without the arrows is not a mechanism. You're just writing stuff. So make sure when you're writing out mechanisms that you use arrows and don't just draw stuff and draw intermediates and things like that. You got to put the arrows in. So that's that. Then I'm going to take the second one and terminate that one. So we know that this is going to be the fastest. All right, because this radical right here is the least substituted. So I can squeeze that in there. Least substituted, so it's primary. All right, and then let's go ahead and do, need to bring all this over. Shrink it. All right, so this is going to be plus, all these are going to be plus a bromine radical. All right, somebody put the arrows in for the second example.
Do you want me to write on it, the screen?
Sure, go ahead.
Okay. Yeah, right.
Okay. So we're gonna get, let me just steal this and just leave those arrows up there for now.
Okay.
I'm gonna steal it and put the product in. So we're gonna get this product with a bromine here. Is that right? Dang it, Russell. Is that right?
Yeah.
Mm-hmm. All right, somebody do C. Anybody, you can annotate the screen and put the arrows in.
I have a question. For the product on the second one, was there something else after the?
Nope.
Oh.
I just copied that when I copied the figure. No, in termination, there's not That's not a secondary, like a side product.
Okay.
Somebody got the third one. Come on now, we got 20 people logged in. So we need at least 2 more people to do C and D. Don't all write at once, it might break the internet.
I can do it again. Sure.
Go ahead.
Okay.
Okay, great. So that product is I'll put the product over on the other side. Let me grab this. That product is gonna look like this. All right. And then what about D? Let's get another person to do D. We just got 20 bodies. So let me put in the arrows for D. We got something for that. Boom here. And then the bromine is here. Now D brings up C and D give us opportunity to add on to what we know about this reaction. We know that the reaction happens faster at least substituted sites. So we can also look at C, and you see that that is a tertiary site. Come on, iPad. That's a tertiary site, so this is going to happen slowest, right? Even though the tertiary radical is very stable, the actual termination part in adding bromine to that site is slow because of sterics, because you got those 2 methyl groups crowding that radical. All right. This one on the bottom also gives us a chance to talk about something. Oh, my bad. Tia, can you take the arrows off? Thank you. This one gives us an opportunity to talk about another aspect of the reaction, which is which out of all of these products, which one is the most stable? How do we tell what's the how do we define alkenes and their stability? Like, what are we looking for? Anybody remember that from part 1? When we talk about monosubstituted, tri-substituted, di-substituted, and tetrasubstituted alkenes?
Like the more substituted it is, the more stable it is.
More stable it is. So when we look at that bottom product and compare the double bond itself, let me change colors on that. The double bond itself to the other double bonds up here. Right? If we look at A and C, those are di-substituted. We look at B, that's monosubstituted. And then here, this is a tri-substituted alkene. So this is going to be the most stable product. We got the fastest form, the slowest form, and the most stable from this example, right? The more stable product is going to be the product with the more substituted alkene, right? Just as a refresher, when you talk about alkene substitution, let me make sure, get your words right, man. right? This is unsubstituted. This alkene would be mono substituted. This would be disubstituted. Why in the world am I not in class? This is trisubstituted. And then this would be tetrasubstituted. I mean, I'm 37 minutes in class. Come on, bro. All right. Questions about that? I feel like I'm teaching in a vacuum. Need some participation.
Can the substitution go higher than tetra?
No, because each one of those carbons in the double bond can only have two things attached to it. So anytime one of those things is not hydrogen, we count that. Or let me not say that, because if you have a halogen or some other functional group, that's different. But if it's a carbon substituent, then we count that as that's how we determine how substituted it is. It's the carbon-carbon bonds on it. So anything past, there's nothing that can go past 4, right? Because the carbon itself, think about it, in the unsubstituted, it looks like this, right? So anytime I start removing hydrogens and adding in carbon, then that's how I count those substituents. So when I start adding in carbon-carbon bonds, that's how I count the substituents. Right, so that's an example. That would be an example of monosubstituted. And then if I put another carbon on there, then that's disubstituted, so on and so forth. All right, that's a good question. All right, let's do this. Let's look at this last, we got time. Let's look at the next example right here. Reaction 2. Tell me, actually I'm gonna break y'all out and let y'all work on this for about 5 minutes. Tell me what your strategy is for this problem.
Find the Allylic sites.
On the Allylic sites, site or sites, right? Let me ask this question. On the allylic site, what is absolutely necessary to do allylic bromination? What do you absolutely need on the allylic site to do allylic bromination?
We need a double bond.
Okay, you need a double bond adjacent to it. But what do you need on the site itself? The whole purpose of allylic bromination is to do what? Let's go back to the original definition of the reaction. What are we doing when we are doing allylic bromination?
Is it alkyl halide synthesis?
And you're trying to put a bromine at the allylic site. Is that right?
Yes.
So how do we do that? We say it's a radical mechanism. You go through initiation, then you get into propagation. When you get to propagation, what do you need at the allylic site in order to do allylic bromination? And so the propagation step is very important, right? Because you can't terminate with bromine until you get through the propagation step. So what do you absolutely need in propagation at the allylic site in order for this reaction to happen?
A radical?
You need to be able to make a radical. That's exactly right. How do you make that radical? Let's stay on that track because you own it.
By homolytically breaking hydrogen.
Breaking a CH bond. So you need a hydrogen at the allylic site in order to do allylic bromination at that site. If there's no hydrogen, you cannot do allylic bromination. So with that being said, I'm gonna take this question right here. You can screenshot it or whatever you want to do. I'm gonna break y'all out into a breakout room, and then I'm gonna give y'all 5 minutes to do the mechanism. We got 20 people. I'm gonna do 5 breakout rooms. And all right, so you should have gotten an invitation to a room. Go ahead and join and take this problem and go through the mechanism. You don't have to show the initiation step. That's fine. That's okay. But you need to do the propagation and the termination steps. And we'll come back at 9:50. All right, if you're not in a room, you need to join a room. You should see an invitation to a breakout room on your screen. All right, we got 5 people still not in a breakout room. Right? Edward, hopefully Farrier, Johnson, Smith, Wilson. You need to join your breakout rooms. If you're still in the main room, you need to find the breakout room that you've been
Oh, yeah, I'm
assigned to.
sorry. I just came back to screenshot, just a screenshot so I could share my screen.
Okay.
So, did you put me back in breakout room 5? Oh, never mind. I see.
All right.